Derivative of the inverse trigonometric functions. Our objective is to find the derivative of the inverse trig functions. Let's start by reminding ourselves of some characteristics of inverse trig functions. Y equals the inverse sine of x if and only if sine of y equals x. Remember, when something's written this way, what is inside the sine function, in this case it's shown as y, is represented as the angle, or is representing the angle, because it's sine of an angle that equals something. The domain for this inverse sine function goes -1 to 1, where the only things that x can be are from -1 to 1. And the range, which is more important to remember, the range of angles is only from -π/2 to +π/2. Now, when we think normally of the sine function, which cycles forever and ever, right? Looks like this, keeps going, looks like that, keeps going. So we've got -π/2 here, +π/2 here. Why are we limiting the range of angles to just -π/2 to +π/2? Well, that's because inverse functions have to be 1 to 1. So we only take this portion of the graph where no x and y's are going to repeat. Just that section from -π/2 to +π/2. If we think of a coordinate plane and the unit circle, I always like to remember all students take classes for the SIGN, positive or negative, of our trig functions. Sine, well, all of them are positive in this quadrant. Sine is positive here and negative here and here. So thinking of our unit circle, we need to pick a quadrant close to 0 that has positive sine values and a quadrant close to 0 that has negative sine values. So that's another way to think of our restriction on the range of angles. So it's important as we think of inverse trig functions that we remember the range of angles. So as you go through practicing, just keep in mind these range of angles are the only ones possible for each of these inverse trig functions. Let's now talk about the derivatives for the inverse trig functions. Let's work on just sine. If y equals the inverse sine of x, we're going to find dy dx. Well, recall that y equals the inverse sine of x means that sine of the angle y equals x. So if I want to find dy dx, I can do so implicitly. The derivative with respect to x of sine of y will equal the derivative with respect to x of x, taking the derivative with respect to x of both sides. The derivative of sine of y is cosine of y, and using the chain rule times dy dx. The derivative of x is 1. So I divide to get dy dx by itself, and dy dx equals 1 over cosine of y. Now, I would prefer to have my derivative of a function of x in terms of x. So let's use our trigonometry to help us with that. We're going to make a right triangle, and we're going to recall our SOHCAHTOA. Remember that y is the angle. So I'm going to put y in one of the acute angles, and remembering that sine means opposite over hypotenuse, so I can think sine of the angle y is x over 1, because that's another way to write x. So again, opposite over hypotenuse. From y, opposite is this side, x, and the hypotenuse is 1. Using our Pythagorean theorem, c squared equals a squared plus b squared, we can solve for that missing side of the right triangle. So we've got our hypotenuse squared, 1 squared, equals a squared, our missing side, plus the other side squared, x squared. Solving for a, we get a to be the square root of 1 minus x squared. So this missing side is the square root of 1 minus x squared. Now, so far in our derivative, we have cosine of y. So what does cosine of y equal in terms of x? Well, cosine is adjacent over hypotenuse. Adjacent over hypotenuse. The adjacent side to y, the leg adjacent, is square root of 1 minus x squared, and the hypotenuse is 1. Or more simply, square root of 1 minus x squared. So we plug that into our derivative, and now we see that dy dx, our derivative, is 1 over the square root of 1 minus x squared. Our derivative with respect to x of inverse sine of x equals 1 over the square root of 1 minus x squared. Our derivative with respect to x of cosine inverse of x is negative of 1 over square root of 1 minus x squared. We could do a similar proof of all of these 6 inverse trig derivatives and see. Most importantly, let's talk about how to use them. Memorize these 6 derivatives of inverse trig functions and learn how to use them properly. Now notice, we really only have 3 we need to memorize because the co-functions of these 3 simply are the same but with the negative. Examples. Find the derivative of each function. Y equals inverse sine of 4x squared. Let's simplify this to call it inverse sine of u. That looks a lot easier, where of course u equals 4x squared. So we take the derivative of y with respect to x using that derivative rule, and we get 1 over the square root of 1 minus u squared, because of course this is a u instead of an x. But because it's a u instead of an x, we must apply our chain rule and say times du dx. Now let's do some substituting. 1 over the square root of 1 minus u is 4x squared, so replacing u with 4x squared, remembering to square it because it's u squared, it looks like this, and then times du dx. What is the derivative of 4x squared? That will be 8x. There is our derivative, a valid answer, but of course we can clean this up a bit. So let's do that. 8x times 1 is 8x divided by the square root of 1 minus 4 squared is 16, and x squared squared is x to the 4th, because 2 times 2 is 4. How about the derivative of y equals e to the inverse sine of x? Now this time, the outside function is the exponential function. All of the exponent is our inside function, or our u. So let's simplify this by calling y e to the u, where u equals the inverse sine of x. Let's write what dy dx equals, and because e to the u is the easiest, we remember its derivative is just e to the u. But of course we apply the chain rule and say times du dx, and now we can do some substitution. This will be e to the, what u equals, inverse sine of x, times du dx, the derivative of inverse sine of x, which is 1 over the square root of 1 minus x squared. This is a valid derivative. It has all x's in it, but we can clean this up just a bit. E to the inverse sine x times 1 is e to the inverse sine x over square root 1 minus x squared. There we have it. Let's take the derivative of y equals inverse tangent of cosine x. Notice the cosine x is inside the inverse tangent function, So we can simplify the way we write this by saying inverse tangent of u, where u equals cosine of x. Now we're looking at the inverse tangent derivative. Let's write dy dx in terms of u. The inverse tangent of u, its derivative will be 1 over 1 plus u squared, and applying the chain rule times du dx. Let's go ahead and substitute the x's back in, and we get 1 over 1 plus, because u is cosine x, this will be cosine squared x, our shortcut way to write it without parentheses, times the derivative of u, which is the derivative of cosine x, or negative sine of x. I like to use parentheses around that so it doesn't look like subtraction. But of course we can clean this up a bit, so let's do so. We get negative sine x over 1 plus cosine squared x. And there's our nice clean derivative. Let's take the derivative of y equals inverse secant of e to the 3x. E to the 3x is of course the inside function. So we can simplify this by calling this inverse secant of u, where u equals e to the 3x. And now we focus on the derivative of the inverse secant function. Let's write dy dx in terms of u. The derivative of the inverse of secant of u is 1 over, instead of x we put u, times the square root of u squared minus 1, and applying our chain rule times du dx. Now let's try to substitute back what we have for u. 1 over u is e to the 3x, so this is e to the 3x, times the square root of u is squared, so that's e to the 3x squared, minus 1, times du dx. Now this presents another challenge because e to the 3x needs a chain rule because it has an inside function, the 3x. So what if we simplified this as e to the v, where v equals 3x? Then du dx is e to the v times dv dx, or e to the 3x times 3. So now we see what du dx looks like and can replace it in here, times 3e to the 3x, which of course is a cleaner way to write e to the 3x times 3. Now we have a derivative, but of course this can be cleaned up quite a bit. We have an e to the 3x divided by itself, and then 1 times 3 is 3, so 3 for the numerator. And in the denominator, e to the 3x squared, we do 3x times 2, which is 6x, so that will be e to the 6x minus 1. What a nice looking derivative. Thanks for watching.